Let's now understand the Euclid's division lemma. Let's observe the following division. Here 4, which is dividing 13, is called divisor. And 13, which is divided by 4, is called dividend. 3 is the quotient, 1 is the remainder. Let's observe the same division pictorially. Suppose you have 13 balls. When you group these 13 balls, each consisting of 4 balls, we will get 3 such groups of 4 balls each, and 1 ball will remain. That is, we can express it as 13 is equal to 4 into 3 plus 1. We can also say that 4 goes into 13 3 times and leaves a remainder 1. Here, 13 is the dividend, 4 is the divisor, 3 is the quotient, and 1 is the remainder. Therefore, dividend equals divisor into quotient plus remainder. Consider some more examples, and write in the format of dividend equals divisor into quotient plus remainder. Here 8 goes into 17 2 times and leaves a remainder 1. Also, we can write 17 as 5 goes into 17 3 times and leaves a remainder 2. Here, 4 goes into 23 5 times and leaves a remainder 3. Here, 6 goes into 35 5 times and leaves a remainder 5. Here, 8 goes into 40 5 times and leaves a remainder 0. So, we can write it in the format of A equals B into Q plus R, where A is dividend, B is a divisor, Q is a quotient, and R is the remainder. In all the cases remainder, R is always greater than or equal to 0, and should always is less than the divisor. So we can write R as 0 less than equal to R less than B. Let's now study Euclid's division lemma, based on this division rule. Theorem 1.1. Euclid's division lemma, given positive integers a and b, there exists unique integers q and r satisfying A equals b into q plus r, 0 less than equal to r less than b. Euclid's division algorithm is based on this lemma. Euclid's division algorithm is a technique to compute the highest common factor, HCF, of two given positive integers. Let us see how the algorithm works through an example first. Highest common factor, HCF of two positive integers a and b is the largest positive integer d that divides both a and b. Suppose we need to find the HCF of the integers 612 and 342. We start with the larger integer, that is, 612. Then, we apply Euclid's lemma to get 612 equals 342 into 1 plus 270. As remainder 270 is not equal to 0, division is continued. Now consider the divisor 342 and the remainder 270, and apply the division lemma to get 342 equals 270 into 1 plus 72. As remainder 72 is not equal to 0, division is continued. Now, consider the divisor 270 and the remainder 72, and apply the division lemma to get 270 equals 72 into 3 plus 54. As remainder 54 is not equal to 0, division is continued. Now, consider the divisor 72 and the remainder 54, and apply the division lemma to get 72 equals 54 into 1 plus 18. As remainder 18 is not equal to 0, division is continued. Now, consider the divisor 54 and the remainder 18, and apply the division lemma to get 54 equals 18 into 3 plus 0. As the remainder equals 0, division is stopped. Notice that the remainder has become 0, and we cannot proceed further. Therefore, HCF of 612 and 342 is the divisor at this stage, that is, 18. So, let us now state Euclid's division algorithm, based on this example.